Morning chemistry. Today is a sad day because we are going over forces of attraction, and I don't get to be with you all to hear all the bad jokes about attraction that you're going to make. However, we'll do our best. I'll try and pause from time to time whenever there's a moment so that you can make a comment to yourself in your room while you're watching this lesson. Alright, so today we're talking about forces of attraction. Now, good news for all of my math-hating people. Yesterday's lesson was pretty much the most math that we'll be doing this chapter. Okay? So if you kind of get down the diffusion, effusion, and the partial pressure laws, that's all the math for this chapter, really. The rest of it's conceptual. So I hope you remember all of that bonding stuff that we did, particularly with covalent bonds, ionic bonds, how to create molecules, because this is what's coming into play big time in this chapter. All right, so forces of attraction. If all particles of matter at room temperature have the same average kinetic energy, why are some materials gases while others are liquids or solids? The answer lies within the attractive forces within particles. They're in love. Just kidding, they're not in love. Sorry. The answer lies, like I said, within the attractive forces because the attractive forces that hold particles together in ionic, covalent, metallic bonds are called intramolecular forces. Not intra. Intramolecular forces. All right? Intra means within. So intramural sports are sports, usually like if you don't play for your college's team or something, you play intramurals. Intramurals means that you're playing other teams also from the college, so within the college. The term molecular can refer to atoms, ions, or molecules. There is a short summary of what you've learned about intramolecular forces in chapter 8 and 9 in the table at the bottom of page 393. I recommend you look at it. It talks about ionic, covalent, and metallic. Helps remind you the difference between all of those bonds, and I would recommend looking over it if you can't immediately tell me what an ionic bond is, what a covalent bond is, and what a metallic bond is. Okay, go look. So intramolecular forces do not account for all attractions between particles. There are forces of attraction called intermolecular forces. So this is within, and this includes ionic, covalent, and metallic. Note that all these are, like it says, within the molecule. So this would be the bonds between the hydrogen and the oxygen in one molecule of water. Now we're going to talk about intermolecular forces. Inter meaning between or among. Okay? So there's three that we're really going to talk about. We're going to talk about dispersion, we're going to talk about dipole-dipole, and we're going to talk about hydrogen bonds. And if those sound familiar, it's because we've actually gone over them before. So dispersion, dipole-dipole, and hydrogen. So these bonds are different because intermolecular forces hold together identical particles, such as the entire water molecule to the next entire water molecule. Okay, carbon atoms such as graphite and cellulose particles in paper, those are held together via the intermolecular forces. The three, yes, are the dispersion, dipole-dipole, and hydrogen. Although some intermolecular forces are stronger than others, all intermolecular forces are weaker than intramolecular forces. Okay, so intramolecular forces are, let's see if we can get out some beautiful artwork here. There's his muscles. They're super strong. Look at that guy flexing. And the intermolecular forces are weaker than those. All right, so let's first talk about dispersion forces. So dispersion forces, recall that oxygen molecules are non-polar because electrons are evenly distributed between the equally electronegative oxygen atoms. Under the right conditions, however, oxygen molecules can become compressed into a liquid. For oxygen to be compressed, there has to be a force of attraction between the molecules, otherwise it won't be compressed. The force of attraction between oxygen molecules is called a dispersion force. A dispersion force is a weak force that results from temporary shifts in the density of electrons in electron clouds. Okay, so dispersion is the weakest. Weak force resulting from temporary, and this is key because O2 is not a polar molecule, but with a dispersion force, it's a temporary shift in the density of the electron cloud. So recall that the electron cloud is where all the electrons are positioned around the atom. When we draw it in a diagram, we make them in a nice circle, but they're not always like that. And so they are moving around. And when you have this temporary shift kind of to one side, to the other, top down, that creates a dispersion force. Dispersion forces are sometimes called London forces, after the German-American physicist who first described them, whose last name was London. Remember that electrons in an electron cloud are in constant motion, though. Okay, so when two nonpolar molecules are in close contact, especially when they collide, the electron cloud of one molecule repels the electron cloud of the other. The electron density around the nucleus is, for a brief moment, greater in one region of each cloud. So briefly, when this is happening, all the electrons are moving and they're reacting. And so this creates a temporary dipole, a temporary moment where within the molecule you have a positive and a negative end. When temporary dipoles are close together, you have the weak dispersion force exists between the oppositely charged regions, right? Because when the electron cloud shifts, you have that positive end and the negative end, and the negative end over here is attracted to the positive end over here, right? Attraction, kind of like magnets. Due to the temporary natures of dipoles, though, because it only reacts from the electron cloud temporarily shifting, they're the weakest. They only play a significant role when there are no other forces of attraction present. Dispersion forces exist between all particles, so all particles have dispersion forces, but they're usually not dominant. These forces can have a notable effect, though, as the number of electrons increases. So the more electrons you have, the more noticeable your dispersion forces are going to be. Okay, so fluorine, chlorine, bromine, and iodine exist as diatomic molecules, right? They're never by themselves because they're going to blow up. They're unstable. There are halogens, right? So fluorine, chlorine, bromine, and iodine are all diatomic molecules. Recall that the number of non-valence electrons increases from fluorine to chlorine to bromine to iodine, right? They go down the periodic table, you get more and more and more and more electrons, right? The further down we are on the periodic table, the more electrons they have. Because the larger halogen molecules have more electrons, there can be a greater difference between the positive and the negative regions. Thus, the difference in the dispersion forces explains why fluorine and chlorine are gases, bromine's a liquid, and iodine is solid. Okay? So, basically, the more electrons present, the stronger the dispersion force. So chlorine and fluorine are relatively small molecules comparatively, and so their dispersion forces are weaker, which is why they're gases. The molecules can't stick together with enough strength to create anything more substantial than a gas. But as you go down the halogens in the periodic table, you get to your bromine and your iodine, and those are they're bigger molecules. They have more electrons. Remember the layers, the S and the D and how as you go down the periodic table you have more and more layers of those, and so your iodine, your bromine, there's so many more electrons there that your dispersion forces are going to be stronger, and so they're going to be able to create a liquid in the case of bromine and a solid in the case of iodine. Okay, hopefully that makes sense. So now let's talk about dipole forces. So this is something that we have covered before, so hopefully it's kind of familiar to you. Polar molecules contain permanent dipoles. That is, some regions of a polar molecule are always partially negative, and some regions of a polar molecule are always partially positive. Attractions between oppositely charged regions are called these dipole forces. Okay? So, attractions between oppositely charged regions of permanent dipoles. Okay, so when one hydrogen chloride, for example, think HCl. Okay, when one hydrogen chloride gas molecules approach, the partially positive hydrogen end in one molecule is attracted to the partially negative chlorine end in the other molecule. How do you know which end's positive and negative? You look at the electronegativity. I think the periodic table with the electronegativity charges on it is in chapter 9, 8 or 9, but I think it's 9, because 9 is covalent bonding. But you can also tell based on the trends of your periodic table. What is the most electronegative element? If you said fluorine, you are correct. Hydrogen is one of the least, not the least, but as you go further away from fluorine in the periodic table, they get less and less electronegative. Okay? So you can see kind of the attraction in the picture on page 394. Basically, your partially negative molecules are always going to, the partially negative end of the molecule is always going to be attracted to the partially positive end of the other molecule. Opposites, right? So because the dipoles are permanent, right, the dipoles that split between positive and negative charge, that's always present. It doesn't depend on temporary shifts in the electron cloud like your dispersion forces do. And so because it's permanent, dipole-dipole forces are stronger than dispersion forces. Okay? This prediction will hold true as long as the molecules being compared have approximately the same mass. Okay? So that's dipole-dipole. Now let's talk about hydrogen. And hydrogen is the strongest of the three intermolecular forces. It's a special type of dipole-dipole bond. So it is still a dipole-dipole because it is still between two permanent dipoles. However, a hydrogen bond is a dipole-dipole attraction that occurs between molecules containing hydrogen bonded to a smaller, highly electronegative atom with at least one lone pair. Now, that sounds specific, and that sounds like you're going to have to be looking, is this one highly electronegative with at least one lone pair? There's three pretty much that it always results in, right? It's usually almost always fluorine, oxygen, or nitrogen, okay? So it's usually hydrogen plus fluorine, oxygen, or nitrogen. Those are your three most electronegative that also have a lone pair that are very commonly found in hydrogen bonds. Okay, so if you have a hydrogen bonded to a fluorine or an oxygen or a nitrogen, doesn't have to be all three, then you're going to have a hydrogen bond, which is your strongest type of dipole-dipole force. Consider, for example, water. In a water molecule, the hydrogen atoms have a large partial positive charge, and the oxygen atoms have a large partial negative charge. There's a big difference in the partial charges between hydrogen and oxygen. When the water molecules approach, the hydrogen atom on one molecule is attracted to the oxygen molecule on the others. And so hydrogen bonds explain why water is a liquid at room temperature while compounds of comparable mass are gases, because those bonds are stronger. The difference between methane and water, if you look at the table on page 395, you see a table. The difference between methane and water is easy to explain because water is these hydrogen bonds, which is the strongest type of force you can get, but methane is only being held together by these dispersion forces, and so it's really weak, so it's going to be a gas at room temperature. So the difference between ammonia and water, though, is less obvious. Molecules of both compounds can form hydrogen bonds. Ammonia is a gas at room temperature, so the bonds in ammonia aren't as strong as the bonds in water, but they are still hydrogen bonds. That's because your oxygen is more electronegative than your nitrogen, okay? So because your oxygen is so electronegative, then the bond between oxygen and hydrogen is going to be stronger because there's a stronger magnetic attraction, okay? So think about the whole good girls like bad boys scenario, right? It's a stereotype and it's not good. But think of it like your hydrogen is your like good girl, she follows the rules, all that stuff. And then your fluorine is like the baddest boy, and so she's most attracted to him, and so that bond is going to be stronger. But an oxygen's like, he's a rebel. And so the attraction there is going to be stronger too. And nitrogen is that guy who like wants to be a bad boy but isn't really a bad boy, and so that attraction force isn't going to be as strong because our hydrogen lady would like a really bad boy. And so that attraction force between hydrogen and nitrogen isn't as strong because nitrogen isn't as bad. Okay? Pretty terrible analogy, but hopefully it helped you get the idea that the bigger difference in electronegativity, the stronger that force is going to be. Okay? So hopefully using all this information, you'll be able to complete today's Junopod. Good luck. And tomorrow we are going to talk about liquids and solids. Okay? So good luck. Like I said, ask me if you have any questions. Your Junopod's going to be due tomorrow. And have an awesome rest of your day, you guys.